Okay, all right. So we're looking at normal random variables. That's our aim. So if we've got a normal random variable, then it's going to be subject to what we call natural variation. So the result is going to be subject to natural variation. Now, as a result, the factors are going to produce a result that is close to the mean. And then the further we go from the mean, then we're going to get the lower the probability. So the frequency density curve, which gives the relative likelihood of probability. So the higher the value of the curve, the more probable the result is. And we call it a normal distribution, is characterized by three key things. Number one, it's symmetrical. Number two, it's what we call bell-shaped. And number three, it's single-peaked. These three characteristics are very important. In exam once they actually asked, how do we know it's a normal distribution? And it was those three things I was looking for: symmetrical, bell-shaped, and single-peaked. And it's fully described by the mean and the standard deviation. So one normal distribution will differ from another. It's got a different mean, or if it's got a different standard deviation, or if it's got a different both. In other words, if it's got the same mean and the same standard deviation, it is the same distribution. That's what we mean by it being fully described by those two things. Now, those that have come in, there are notes on the table if you need them. And the other key thing is it's got this rule which we call the 68, 95, 99.7% rule. Now, what that means is that approximately 68% of the data will fall within one standard deviation of the mean. Approximately 95% of the data will fall within two standard deviations. And approximately 99.7% of the data will fall within three standard deviations. Now, there are two ways to interpret what I've just said. We could say, as I've said here, that 68% of the data will fall within one standard deviation of the mean. And I'll explain this in a little more detail. But the other way to think of it is, given one particular value, there is a 68% chance, or the probability is 0.68, that that value will be within one standard deviation of the mean. So there's two ways. We can talk about it as a percentage of the data, or the probability that one value will fall within that range. I'll emphasize this again because there is two interpretations and you need to understand both to actually be confident with what we're doing. Different ones will expect different interpretations. So, the equation of the normal curve. Now remember, when we were given continuous random variables, we were actually told what the probability density curve was. We were given an equation. So the equation for the normal is 1 on sigma, sigma being my standard deviation, times by the square root of 2 pi e to the power of minus a half, x take mu, mu being the mean, on sigma squared. So mu is the mean, sigma is the standard deviation. Now, it's not a very nice equation, but it's one that works for us. Now, what you would find if you were to differentiate this equation, and you could differentiate it, is that you would find that the maximum value occurs at mu. So this is a generic equation for some mean and some standard deviation. This is a normal distribution for the mean being mu and the standard deviation being sigma. We're keeping it open. You would find that the central value and the maximum value occurs at mu. You would then come one standard deviation out, and you would then find that this is mu take sigma and mu plus sigma. And in this range here, we have 68.26% of our data lying there. In other words, if you were to find the area between these two vertical lines here, the area under that would be 0.6826. In other words, it would be 68.26%. If you were then to come out to mu take 2 sigma and mu plus 2 sigma, and you were to find the area there, you would find that we have 95.44% between those two vertical lines, mu take 2 sigma, mu plus 2 sigma. And then finally, if you were going to go all the way out to mu take 3 sigma and mu plus 3 sigma, you would find between those two vertical lines, we then get 99.74%. So what does that mean? Well, remember there are two ways to interpret this. If you have a discrete random variable, rather a continuous random variable, let's say the heights of you guys, it would roughly be a normal distribution. 68% of you guys would fall within this range. You'd be about mean, probably around 170, 180. 95% of you guys would fall between this range. Remember that 95% includes the 68%. 95% of you would be in here, and then if we went right out to these lines, that would capture probably almost all of you, 99.74%. Potentially some might sit outside. That would be about it. Not very many of you would fall outside that range. Now, that's one way to interpret it. The other way to interpret it is, let's say I randomly picked one of you. There is a 68% chance that you will fall between these two lines, that one person that I picked. There is a 95% chance that you will fall between these two values, and then there is a 99.7% chance that you will fall between these very extreme values. So, which makes sense. The bigger range I take, the more probable that you'll fall in that range. That's what we talk about when we talk about two values, or two ways to interpret it. Okay. Now, a couple of key things to note. The mean, median, and mode of a normal distribution are the same. There is no difference. They all lie along that middle value, that central value. We can understand that because the mode is given by the maximum value. That's where our continuous random variable curve is at its peak. The median, well, it's symmetric on both sides, so that kind of makes sense. And we'll get 50% of our data occurring right there. And then finally, the mean, well, that falls in the middle because we have a symmetric distribution. Symmetric distributions always force their mean to occur in the middle. It's symmetric on both sides, the mean will always occur in the middle. The other thing we need to know is that the graph is asymptotic. To the x-axis. And the area between the normal density curve and the x-axis is equal to 1 unit squared, as it has to be. The area below the curve has to equal 1, or else it's not a valid continuous, it's not a valid function for a continuous random variable. So what that last thing means is if I integrate from minus infinity to infinity, which is quite hard to do, of 1 over sigma root 2 pi e to the minus a half x take mu on sigma squared, that equals 1. Now, why am I going, let me just explain this. Why am I going from minus infinity to infinity? Well, remember we said that it's asymptotic to the x-axis. So this function never actually crosses over the x-axis. It's greater than 0 for all values from minus infinity to infinity. So this function exists for all real values, which means we need to integrate from minus infinity to infinity. It exists for all those values. And if we do that, then we're actually going to go through and get 1. Now, don't fall into the trap of trying to prove that for yourself, okay? You can't actually integrate that function. In fact, nobody can integrate that function unless you do some pretty tricky stuff. I did it at uni and we changed variables and did all sorts of stuff. So you don't need to worry about it. You will never be able to integrate that and show that's 1. Okay, so is it a valid probability distribution function? Is it continuous? Does it jump? Or does it break at some point? If you look at the function, I've got just 1 on some values where sigma is never going to be 0, and it's just e to some values. Am I going to get an undefined value? No, I'm not. I said sigma is never 0, so we're never going to get 1 on 0, and e to any value exists for any real value. So I'm never going to get something that is undefined, so it's continuous. Is it positive for all values? We go back up to the graph. If it's asymptotic to the x-axis, then it creeps up to the x-axis, but never goes through the x-axis and crosses over. So yes, it is always positive, and we've already said that the area is 1. So yes, it satisfies these 3 conditions for a continuous probability density function. So, if x is a distribution of a continuous random variable, which follows a normal distribution, with a mean of mu and a standard deviation of sigma, then to emphasize what we've just said mathematically, we write x tilde n mu comma sigma. It's like when we were doing the binomial. We would write x tilde bin np. So because a binomial got fully described by the number of trials and the probability of success. So in this case, x gets fully described by the mean and the standard deviation because we know it's a normal distribution. Yep. Yep. So yes, you can choose which one you do, but I always just do mu sigma. I just think that's easier. Yes, sometimes the book has sigma squared, but it will always write it as, so if you go x and 5, 4 squared like that, then you know that the standard deviation is 4. They will never write it like that and expect you to square root it. Okay, they'll never write it like that. So whether it's x tilde n 5, 4 or 5 and 4 squared, either one of those is right. SACE never actually use any of those. So there's going to be no confusion in the exam which one they're doing, because what they'll say is x is a normally distributed variable with a mean of 5 and a standard deviation of 4. They will give it to you in words, they won't give it to you in those math symbols. Okay? But you can use those because it's easy and it can communicate quickly to the marker what you're actually thinking. So that's going to actually be useful for us. But SACE won't actually use it. Markers will know what you're saying by that, but they won't use it themselves. Okay, so I've got the normal probability density curve shown below for the distribution x, n, 10, 100, or 110 rather. So we've got a standard deviation of 10, and we've got 100 coming out at, we've got our main value at 100. Now, I don't think you got this graph printed in your no. So what I want you to do is I want you to draw something roughly like that. Make sure that you give yourself a bit of a scale along the bottom, and make sure that you do this to a very defined height with plenty of space above it. So you're going to need similar space to what I've got there. So give yourself plenty of space above it and make sure you draw a curve roughly like that. So give yourself a scale along the bottom as well. I'll give you a couple of minutes to do that. If I'm looking to draw x1, which is normally distributed with a mean of 60 and a standard deviation of 10, my central value is going to have to be at 60. Now when I hit 3 standard deviations away from 60, I need to be on pretty much at the x-axis or very close to it. So 3 lots of my standard deviation is 3 lots of 10, which is 30. So I'm 30 away from 60 here and 30 away from 60 here. So when my graph gets to 30 and 90, it has to be very close to the x-axis. So then I can just draw it. Like that. You could argue that that's not very good, and no, it's not, but you get the general idea. You should show a clear inflection point, roughly, so it's changing from concave to convex. There, my inflection point's probably a little too late, but I'm not going to worry about it. Your main things are that it's getting close to the x-axis at the right point, and your height. We'll talk about the height in a second. If I'm looking to do this next one, x2 at 110 on 3, well, my mean's going to be at 100, and it'll be getting very close to the x-axis at 3 lots away. 3 lots of my standard deviation away. 3 lots of 10 on 3 is what? If I times 10 on 3 by 3, what do I get? 10. So at 10 away from 100, I need to be pretty much on my x-axis. That means at 90 and 110, I need to be pretty much on my x-axis. So this is going to be squashed up. But to ensure that I've got an area of 1, I cannot keep it the same height. As I bring the sides in, the height has to go up to preserve my area of 1. And it will go up by the same factor. So it's come in by 3, it'll go up 3 times. So here, if I go according to these lines on here, I'm at 2.5. So I need to go up to 7.5. So this is 1, 2, 3, 4, 5, 6, 7.5. I need to go up 3 times because my sides have come in 3 times. It is that prescribed to preserve the area. Now, I can't quite fit it on this, so I'm just going to make it a bit smaller. And it's quite hard to draw. You get the general idea. It's gone 3 up because it's come in 3. Okay, on the last one, how much is the standard deviation decreased by from 10? It's 5. So what factor has it decreased by? 2. So then we need to multiply our height by 2. So it's going to be double what it is here. And we're going to be centered at 120. So I'm going to be there, twice as high. And my standard deviation is going to be, so by my standard deviation, it's going to be very close to the x-axis here and here. So my standard deviation is 5, which means at about 15 on either side, 3 lots of my standard deviations, which is 15, it'll be very close to the x-axis. So there and there. No, I went too far that one. So over there and there. Okay, so it will look like that, and so that is twice as high. Because our standard deviation has been halved. Bring the sides in, push the height up. Take the sides out, bring the height down. You've got to preserve your area of 1. Okay, let's move on. Okay, alright. Coca-Cola vending machine is set up to give a mean fill of 250 mils per cup. The amount of Coca-Cola dispensed is normally distributed with a standard deviation of 15 mils. Remember I said they won't use that notation in an exam? This is the way they give you the information. So formally define the random variable and write an expression for the distribution. So we can say, let x be the amount of Coca-Cola dispensed per cup measured in milliliters. So x is normally distributed with a mean of 250 and a standard deviation of 15. Now for a continuous random variable, like a discrete random variable or for a normal distribution, we can always start off with let x be the amount of, and then you give the quantity, and then you say measured in. So that can be your setup for defining any random variable, and you just need to fill in the specifics of the actual question. So Coca-Cola dispensed per cup and measured in milliliters. Okay, show an appropriate scale for the normal distribution below considering it models the context. So our mean was 250, so that's going to sit in the middle. Then one standard deviation away means I'm going up 15, so I'm then at 265. Another standard deviation means I'm going up another 15, so I'm at 280. And then going one more standard deviation means I'm at 295. So I'm just going up 15 each time, and I'm picking on 15 because that's our standard deviation. Coming back the other way, I come down 15 to be at 235. I come down another 15 to be at 220. I come down another 15 to be at 205. Now, if I draw my vertical lines in, I can fill in specific areas on my graph. So the values here, so between these two vertical lines I need 68.26%. So each of these, because it's symmetric, I'm going to account for 34.13%. Then these values are going to count for 13.59%. And then the very edges are going to count for 2.15%. And then outside 3 standard deviations on either side is going to account 0.13%. Okay, right. So using your graph, determine the probability that a randomly filled cup will contain between 235 and 265 mils. Remember, this situation, we can be interpreting these percentages as proportions or probabilities. In this case, we're doing it as probabilities. So 235 and 265 are those values there. So the probability that x is less than or equal to 265 greater than or equal to 235. Well, I've got 34.13% there. Plus another 34.13% on the other side of the mean. So I'm just adding these two values because that gives me the probability that it would be between those two values. It gives me 68.26%, or expressed as a decimal, that's 0.683. So there's a 0.683 probability that a cup will contain between those two values. Probability between 235 and 280. So 235 is there, 280 is there, so I'm just going to have to add on this 13.59%. So the probability that any cup will be between 280 and 235 will be 68.26% plus 13.59%. So that's 0.6826 plus 0.1359, which is going to give me 0.816. So there's a 0.816 chance that the cup will contain between 235 and 280, so between those two values there. It's probability. The other way to look at it is that 81.6% of the cups will lie within this range. That's a proportionate interpretation. Now, I'm sure you'll be very glad to know that we can do all of this on the calculator. So everybody get your calculators out. Find the probability that a randomly filled cup will contain between 242 and 269. So 242 does not lie on my graph, it is about there, and 269 also does not lie, is not one of the special values on my graph. So 242 is about there and 269 is about there. So there's no way we could actually use our graph to do this. So we're going to need to use our calculator. Now the record of the value of how we do it is there, but I'm actually going to go through it on the calculator, and there's no difference between old and new calculators like there was with binomial. It'll work the same for everybody. So 242 and 269. We go to statistics, which is number 2. Go to F5 for distribution. Now, as last time we picked binomial, this time we're picking normal, right down the end. And NPD never gets used. We never find the probability of a single value. We'll always use NCD or INVN. So we're picking NCD. We make sure our data is set to variable, not list. Our lower one was 242. Our upper one was 269. Standard deviation was 15, and your mean was 250. I go through, it gives me 0.600. So, the probability that a cup will be between 242 and 269 will be 0.600 into 3 significant figures. Find the proportion of cups which are likely to contain less than 225 mils. Notice that's actually changed. The wording of the question has changed. Here it's find the probability that one cup will lie in this range. Now it's proportion. So out of all the cups, how many or what percentage of the cups or what proportion of the cups are going to contain less than 225 mils? So there's a probability that X is less than 225. Now, $225 is about there, and we're going to go everything less than that. So, if I go back to my calculator, my upper is going to be 225 because I'm going everything below that. And my standard deviation and my mean will remain the same. But, as my lower value, remember we said that the normal distribution goes on forever. It asymptotes to the x-axis so it never finishes. Now, there's no button for infinity in here. So basically go to the lowest number the calculator can handle, which is -1 e to the 99. That's basically -1 with 99 zeros after it, and that's a really, really low number. So -1 e to the 99 is our lowest value that our calculator can handle. And we get enter, and we get 0.0478. So the probability that X is less than or equal to 225 is 0.0478. And let's just take a record that we said that the lower was -1 e to the 99. People know how to get -1 e to the 99? So the E button is down next to the minus button. EXP stands for means times 10 to the power of. Okay. Now, as I said for binomial, recording what you actually entered into the calculator has is of no worth. Okay? There is no marks awarded for what you enter into the calculator, so don't bother wasting your time. If the total capacity of a cup is 300 mils, find the percentage of cups that will overflow. So 300, so 300 sits out about here. So it's everything after 300 that will overflow. Now, if I go back here, this time my lower is 300 because I want everything above that. Now for my upper, instead of it being -1 times 10 to the 99, it's going to be +1 times 10 to the 99. So it's going to be 1 e to the 99. And so I get 4.29 times 10 to the -4. So the probability that X is greater than or equal to 300 is 0.000429. And let's make a note that our upper was 1 e to the 99. Any questions about that? So predominantly this is going to be calculator work. It's rare that you're going to be asked for those values, but sometimes you may be.